Okay, we are going to continue on here. So last time we wrapped up solutions, I believe. So we are off to chapter 10 here, which is acid and bases. Also, it is the last chapter that involves a calculator. So this is it. After this, we go into organic, and you could put your calculator to bed at that point. You don't have to use it for anything. So this is the last one that does involve calculations. There are obviously some good amount of calculations in this chapter. And then we will very shortly roll into organic chemistry, which is chapter 11 and on, I think, at that point. All right. So let's talk a little bit about acid and bases. Acids are really solutions that are able to produce H plus ions in the actual solution. Bases, as we'll talk about, are really the guys that can produce hydroxide. We talked about some naming of other stuff. It's a good idea. I'm just going to kind of go over how we go about naming acids. In case you ever come across one, you don't have to say like that thing over there or whatever that is. So just really quickly, in terms of acids and how we name them, they are a little bit different than bases. Bases are pretty much just named because a lot of them will have hydroxide in them. You just name them like you normally would, like sodium hydroxide, potassium hydroxide, kind of like a polyatomic ion type naming. But really, when we go to name acids or you see a formula for an acid, it really all involves whether or not pretty much oxygen is there. So the big thing is whether or not the acid has oxygen. And if the acid does not have oxygen, so no oxygen, the way the acid is named is it starts with hydro. It is something ic acid. Now, pretty much all acids, the cation for all acids is basically H plus. So the anion is the negative guy, but the cation pretty much for all acids are H plus. And the missing part here is really the negative part of it. So if we had something like HCl that has no oxygen in it, and it is an acid, so this would be hydrochloric acid. Again, obviously the chloric part coming from the chloride there, that's the negative ion. If we have HBr, that would be hydrobromic acid. So a lot of your group 7, your HF, hydrofluoric, HI, hydroiodic acid, a lot of those guys are acids that do not have oxygen in it. What makes something an acid is really it's an aqueous solution, so it typically has the aqueous symbol next to it. If that had HCl with a G next to it, like a gas, it would be called hydrogen chloride. You take some hydrogen chloride, put it in some water, it then basically dissolves in the water, and you get hydrochloric acid, which obviously is an acid. So most acids should have like the aqueous symbol next to it to imply it's in solution. And anybody without an oxygen, that's how you name it. Now, if it is yes, it does have an oxygen, it pretty much will contain one of those polyatomic ions. And if you remember, really those polyatomic ions ended in one of two ways. They either ended, most of them, in ate or ite. And when we look at an acid, if the polyatomic ion ends in ate, the acid is something ic acid. So like HNO3. NO3 is NO3 minus, which is nitrate. So this is nitric acid. H2SO4. SO4 is sulfate. This would be sulfuric acid. And kind of the same rules apply with acids. They are really sort of treated like an ionic compound, even though in reality they're not really an ionic compound, but they're treated like an ionic compound. And that is why in the second case here, we have 2 hydrogens because sulfate's -2 and each H plus is 1. So you need 2 of them to balance out the charge to 0. So it kind of works the same way. That's what we were talking about with ionic compounds. Now, if your acid does contain oxygen and the polyatomic ion ends in "ite," it is something OUS acid here. So if we took something like HNO2, NO2 is NO2 minus, which is nitrite. This would become nitrous acid. Let's see here, H2SO3. SO3 is SO3 2 minus, which is sulfite. This would be sulfurous acid in this case here. So this is again the way you kind of name these guys. As you can see here, if it does have oxygen, you should not use hydro. Hydro is specifically for acids that do not contain oxygen, and obviously ick or OUS. You know, you ate too much, you feel icky is a good way to remember that, and that is how you name those acids. Any questions on that? So again, that way when you see an acid, you hopefully know what the name should be. All right, then let's get into actually some of this stuff here. Let's talk a little bit about some characteristics of acids. Yes, I can. Yep. There is not. So now we don't use any really prefixes. If the polyatomic ion had sort of a prefix or something in it, you would still keep it. So for example, if you had HClO4, which is a strong acid, ClO4 is ClO4 minus, which is perchlorate, and you would actually still keep the per part of it, and this would be perchloric acid. Again, still ending with the IC because it's perchlorate, and you would keep that. Just like if you had HClO, the ClO is ClO minus, which is hypochlorite, and this would be hypochlorous, chlorous acid in this case. So, you know, if the polyatomic ion had sort of a little weird beginning to it or that type of name, that would be the only place that you would keep something like that. You wouldn't insert any type of mono or any of those type of prefixes. Good? Yeah, okay. All right, so let's talk about some characteristics of acids or bases. So acids have a sour taste. Obviously, don't taste any acid or bases in lab, right? They cause changes in plant size. So sometimes we use litmus paper, and maybe you'll use it next week. And so, but litmus paper is basically, like it says, plant dye, and it does change color depending on whether it's sort of an acidic or basic solution. So typically, if you take any type of litmus paper, be it red litmus paper, blue litmus paper, or neutral litmus paper, basically, if it turns red or stays red, that basically means it's an acidic type of solution that you're dealing with. They react with certain metals to produce hydrogen gases. So single replacement reactions, we see that. So something like zinc plus some hydrochloric acid will do a single replacement reaction where it will come in and kick out the hydrogen. And when it does, it will make a new ionic compound, which is the zinc chloride, and produce that hydrogen gas. And I'm sure along the way in your reactions lab, you probably did this one, either that or magnesium or something like that with the hydrochloric acid. They also will conduct electricity really well. Strong acids are strong electrolytes. Weak acids are weak electrolytes. And again, obviously, as we talked about with electrolytes, if it's a strong electrolyte, it will conduct electricity really well. The sort of implication for acids in this sort of chapter is if it's a strong acid and a strong electrolyte, it basically will 100% break apart in solution and really not stay together. And that's really important for why it is a strong acid. They also will react with carbonates, acids, to produce carbon dioxide. So if you react some hydrochloric acid with like some sodium carbonate here, it will do a double displacement reaction and you will get H2CO3 plus some sodium chloride in this case. This H2CO3 is carbonic acid. The CO3 is carbonate, hence the name carbonic acid. This will go through a decomposition reaction really quickly and produce H2O plus some water, plus some CO2. There we go. CO2 plus some water. And it will produce this sort of CO2 gas, plop, plop, fizz, fizz, kind of like an Alka-Seltzer sort of deal, right? And you get all those bubbles and stuff like that. Kind of a similar reaction occurs. Now, bases, on the other hand, they have a bitter taste. They do feel very slippery. If you ever got a base on your hand, it feels pretty much like soap, or you have like a layer over it. I know somebody handed me a base once in my bare hand, and I was really thrilled about it. But it felt like I had a nice layer of, something over my hand. A lot of soaps, a lot of drain cleaners, those type of things, they're really bases. You could go like Home Depot and buy like pretty much sodium hydroxide to clear your drain and stuff like that. They also will change litmus paper, except that if it's basic, the litmus paper pretty much will turn blue. So if you have any type of litmus paper that turns blue, or I guess stays blue, it is a basic solution. Also, just like acids, strong bases will conduct electricity really well. They're strong electrolytes as well. When we talk about bases, the word alkaline is used a lot. And alkaline means basic. And if you think about group 1 and group 2 on the periodic table, group 1 is the alkaline metals, group 2 is the alkaline earth metals. Those guys are pretty much where a lot of our strong bases come from. And again, that word alkaline means basic. So if they were saying instructions, make it alkaline, they're basically saying make it basic in terms of the pH. So let's talk a little bit more about acids. So acids are basically substances that will produce H plus ions in solution. H plus ions are sometimes referred to as protons in acid-base chemistry, and that is because hydrogen has basically one proton, one electron, and no neutrons. So in order for something to become positively charged, it needs to lose an electron, which leaves hydrogen just a proton, which is why it's called a proton in this case. Now, throughout sort of this chapter and pretty much throughout acid-base sort of chemistry, the H plus, which is the hydrogen ion, or a proton, and H3O plus, which is the hydronium ion, which is like a polyatomic ion. These guys are pretty much used interchangeably. So anywhere I write H plus, which I kind of use H plus most of the time, you pretty much could substitute H3O plus for it. It basically means the same thing. It means basically the acid part of the solution. So H plus, H3O plus used interchangeable in sort of reactions and also interchangeable in formulas as well. So again, you could pretty much just straight up substitute those guys in most cases. The reason you get both of those has to do with basically, sort of how people sometimes will write a reaction for like an acid. If we took something like hydrochloric acid, which is a strong acid, we could show it breaking apart by simply just writing it almost like an ionic compound where basically the H plus and the Cl minus comes out. Another way that people will sometimes write the exact same thing, which is really just hydrochloric acid by itself, is they will include water in the equation. And when you do include water in the equation, what you end up with is H3O plus and Cl minus. And that is because the H plus is coming out over here, basically. So these are two ways you can represent really the same thing. This is just really the acid breaking apart in water, and this H3O plus and the H plus are basically, for all intents and purposes, the same thing. Yeah. So like I said before, personally, I use H plus a lot. And again, you could just swap out H3O plus. textbooks and stuff tend to use H3O plus a lot. So again, they are very much interchangeable. Any questions on that there? Okay, so strong acids, as I mentioned, are strong electrolytes. And if you remember, strong electrolytes pretty much mean when they go for a swim, they will 100% break apart into ions. So when we have something like this guy here, which is nitric acid, when it's actually in solution, it will 100% break apart into H plus and nitrate ions that are floating around in that solution. You have absolutely none of the HNO3 units still together when it's in solution. It has 100% completely broken apart into those H plus and nitrate ions. That is also why this is considered a strong acid, because pretty much all it needs to do is go for a swim and it's going to produce a bunch of H pluses really quickly. And that basically is your definition of an acid, is something that's able to produce those H pluses. So again, as soon as it kind of goes into the solution, you got a lot of H pluses really quickly. Again, why it is basically a strong acid. These are some examples of strong acids: HCl, hydrochloric acid, nitric acid, sulfuric acid. One that I put up earlier, perchloric acid, is a strong acid. Hydrobromic acid is a strong acid. Hydroiodic acid is a strong acid. These are, for the most part, most of your strong acids that you come across. So these are, maybe 6 or so here that are good to sort of remember that they are strong acids, in case you ever have a question like that. Anything outside of this list, probably almost a safe bet to assume that they are probably going to be more of a weak acid. So these kind of 6 here are, kind of the major ones that we do see in terms of sort of strong acids. Any questions on that? And that means every one of those up there will pretty much 100% break apart into ions when they go into solution, again producing a lot of H plus really quickly, and thus again making them a strong acid. Now, bases, on the other hand, are substances that can produce hydroxide ions in solution. So kind of a little bit opposite of an acid is pretty much if you have something that has the ability to produce free OH minuses floating around, or hydroxide ions floating around in that solution. That is really your kind of basic definition of something that is a base. Strong bases, just like strong acids, are strong electrolytes. They will 100% break apart in solution. So something like sodium hydroxide here, which is a strong base, in solution 100% breaks apart into the ions. Again, you have none of these units still together. And again, that is why it's considered a strong base, because as soon as it goes for a swim, you've just generated a lot of OH minus really quickly in that solution, and thus it will probably make the solution basic because of that. Now, a lot of these strong bases, as I mentioned before, do come from kind of group 1 and group 2 on the periodic table. And if you look on the periodic table, kind of like lithium, then we got a little sodium and potassium, then kind of hang over there to calcium, strontium, barium. These guys here with some hydroxide in the formula, probably a lot of strong bases are those guys right there, where you can find them again, group 1 and group 2 on the periodic table. Also, I want to, not 100% of the time, but pretty close. If you kind of see something with hydroxide in the formula, it's almost a safe bet to think of it as a strong base. Again, there are some exceptions, but for the most part, most of those guys that do have hydroxide in it are a strong base. Now, not all bases are necessarily strong bases. There are some weak bases, and they are still considered weak. They're still considered bases because they're able to actually produce hydroxide. A common weak base, for example, is something like ammonia here, NH3. NH3, when it is in water, will basically pick up a hydrogen from this water and make NH4 plus, which is ammonium. And more importantly, it will produce some hydroxide here. So something like ammonia, which is not necessarily carrying the OH minus on board, if you will, it can go through a reaction with something like water and actually produce OH minus, and is still considered a base because of that. It is a weak base because, frankly, it's got to go find some water, do a reaction to produce the hydroxide. Something that's a strong base, pretty much, like I said, kind of has the hydroxide ready to go. And once it goes in, it just releases it. So it doesn't have to do all that kind of work. So something like ammonia would produce obviously a lot less hydroxide in most cases than something that is a strong base. Any questions on that there? So we talked about sort of reactions to strong acids and base, but let us talk about it again. A reminder that when we take a strong acid plus a strong base, we basically get two things. We get basically salt and water is basically what is formed. And really the water is formed as a result of the H plus that comes from the acid and the OH minus that comes from the base is basically how we make the water. So the base kind of contributes the OH minus, the acid contributes the H plus. Whenever you put H plus and OH minus together, you basically make water, is basically what the outcome of that will be. And that is true, you know, if we take something like hydrochloric acid, which is a strong acid, plus sodium hydroxide, which is a strong base. Remember that these type of reactions fall under the big umbrella of double displacement reactions. So you could think of this again as a positive, negative guy, positive, negative. And again, the positive will switch partners there. So the H plus and OH minus will come together. And again, that is how we get our water. And then the salt is the result of the other guy switching partners. So the sodium and the chloride would come together, and that would make our sodium chloride here. And obviously that would be our salt in this case. So a salt is really just a ionic compound that is, for the most part, the spectator ions that are hanging out, just kind of watching everything happen. The fundamental thing that is going on when you react a strong acid and strong base together is you're making water. So as we probably talked about when we talked about types of reactions, one of the reasons why a reaction takes place is to form water, is one of the reasons why it takes place. And that is definitely what is happening whenever you mix a strong acid and strong base together. The ultimate change that's occurring is really what we see here. This is what is sometimes referred to as the net ionic equation. And ultimately it is the H plus from the acid reacting with the OH minus from the base, basically to form water. Any questions on that there? So if we look at this equation a little bit closer, we can break it apart into what is sometimes referred to as the ionic equation or the total ionic equation or complete ionic equation. And basically, because hydrochloric acid is a strong electrolyte, it will 100% break apart into ions, which is H plus and Cl minus, basically. Sodium hydroxide, which is also a strong electrolyte, will break apart into a sodium ion and a hydroxide ion. Now, water, which is a pure liquid, is bound together through sharing of electrons. It won't break apart really in the solution, so we keep it together here. But sodium chloride, which is our salt and an ionic compound, will break apart into a sodium and a chloride. This again is what is sometimes referred to as sort of the total ionic equation or complete ionic equation. This is really what's happening like in the beaker, if you will. You got all these guys basically floating around, you know, in solution. And at some point, these guys will go, cool, I'd like to come together and make some water there. And that will leave the sodium ion and the chloride ion still floating around basically in the solution. When you look at an equation like this, you can look on the left-hand side or right-hand side, and you can actually find a couple of ions or so that are exactly the same. And in this case, that is the sodium on both sides, and that is the chloride on both sides. And these guys are what are referred to as spectator ions. So what are spectator ions is very much like the name implies. If you are a spectator, you are just watching. And that's basically what is happening there. They're at the ballpark, but they're in the stands. They're not on the field playing. Yes. So they're just watching. They're not leading to any of the product that is being formed. And in a solution, if you put these together, you would make water. There still would be the sodium ions floating around and the chloride ions floating around. And that's because in this particular case, they are soluble and they won't make anything, no solid or anything form. So typically what we could do is just cross out those spectator ions, and what we are left with is the net ionic equation that we saw on the previous page, that ultimately this is the reaction that is occurring every single time that you put a strong acid and strong base together, regardless of what combination of strong acid, strong base. If you kind of go through the complete ionic equation, get rid of all the spectator ions, that is 100% of the time always where you end up, H plus plus OH minus, making water, which again is one of the fundamental reasons why a reaction takes place. Any questions on that there? Okay. Here's some more examples here. Here's our nitric acid, which is a strong acid. That is potassium hydroxide, which is a strong base, makes water, and a salt here, which is our potassium nitrate. This again is still a double displacement reaction. It is the hydrogen that's positive coming over to the hydroxide that's negative. And it is the potassium coming over to the nitrate there. And again, if you took that guy also through the same type of equations, you will end up with H plus plus OH minus makes water. Now, sometimes though, you got to remember that, you know, it is ultimately a double displacement reaction. You always make water, but what we're looking at here, these two acids, for example, are what are referred to as being monoprotic. And a monoprotic acid is basically an acid that pretty much, mono meaning one, right? Protic meaning proton. It basically has one H plus to give. So monoprotic means it has one H plus to give. You could have something like sulfuric acid that we saw a little bit earlier there. It's got actually two hydrogens to give, and this is what is sometimes referred to as a diprotic acid. Now, why is that important? If we took, say, sulfuric acid here, and we reacted it with our sodium hydroxide. This again is positive, negative, positive, negative. So we are going to make water, and that is going to be the H plus and the OH minus coming together here. And then the sodium and the sulfate are going to come together. And when we put it together, we want to make sure we put it together correctly. So sulfate has a what type of charge? It is a -2 charge, right? Sodium has a +1 charge. So the correct formula when we put that together is Na2SO4 in this case, right? We want to make sure we balance it out correctly, just like we do with nomenclature. At this point, we could actually balance the equation because it's not balanced at this point. We could lay up a 2 there and maybe like a 2 there. And now we have the actual balanced equation. So, you know, it's important if you have to predict what's on the other side. Again, this is our water and salt. It's always going to be water, and it's always going to be a salt. And essentially what you could do is just go to the acid and just cross out the H, go to the base, cross out the OH, and then that is basically where your salt's going to come from, putting those guys together in the proper way, just like with, you know, to balance out the charge to 0. So, you know, that's pretty much always where water comes from, that H plus from the acid, OH minus from the base. So you can put your hand over those two and then just put the other two things together correctly and then balance it. So it's important to do it in that order. not balance and write the formula. You want to write the formulas correctly first and then balance the equation if you have to predict what's on the other side and then balance it up. Any questions on that there? Okay. So let's talk a little bit about some more specific definitions of acid and bases. The first sort of early definition was one done by a guy named Arrhenius. He did a lot of work with electrolytes, and he simply sort of defined an acid as, again, something that is able to produce that H plus or hydrogen ion in solution, and a base is something that's able to produce hydroxide. And the idea here is what we're talking about when we talk about producing a solution is these things need to be sort of freed up and kind of floating around by themselves. So something that's able to free up an H plus and just kind of release it into the solution so it's floating around, or something that's able to kind of free up some hydroxide in solution and allow it to sort of float around is really what we're talking about. It's not really attached to anything else at that point. It's just sort of free floating in the solution. And these were really good sort of definitions of an acid and base, but he did a lot of work with electrolytes and strong electrolytes. And he focused in a lot on bases that actually had hydroxide in the actual sort of formula, if you will. And as we saw a little bit earlier, not all bases have hydroxide in it. So a more general definition of an acid and base is one that sort of came out of that. But here again is sort of his definition. Like I said before, if we take some hydrogen chloride gas, kind of bubbled it in water, that is where you produce your hydrochloric acid. Same thing, you take some solid sodium hydroxide and dissolve it in water. That's going to create these aqueous ions. And again, it is the creation of these free H plus or OH minuses that essentially make it an acid or a base. So, like I said, it was a really good step forward, but he really sort of focused in a lot on just one type of base with the hydroxide. And not all bases do contain hydroxide. So a more sort of general definition that you could sort of apply to, even things that do not have hydroxide in it is what a lot of people sort of look at when we talk about acid and bases. And this is the Bronsted Lowry definition of an acid and a base. And in a Bronsted Lowry definition of an acid and a base, an acid is a proton donor, which means it is the thing that gives away an H plus, and a base is a proton acceptor. So this is pretty much usually the definition that people sort of refer to when we're talking about sort of acid and bases, and it involves really the transferring of an H plus from one place to the next. It's also really important to understand the concept that these things happen basically one H plus at a time. So things get transferred as one H plus at a time, no more than that. So an acid will give up an H plus and really a base will accept an H plus again in almost a stepwise fashion. It will happen basically one step at a time. Even an acid like the diprotic acid that we were talking about there, the sulfuric acid, even though technically speaking, it's got two H pluses that it could lose, it actually does lose each one individually. The first thing that would happen is it would drop off one H plus and maybe give it to somebody, and it would produce HSO4 minus. And then the next thing that would happen is that HSO4 minus would drop off the second hydrogen and make sulfate. So, sometimes people think, like, for example, something like sulfuric acid, that it just kind of dumps both of the hydrogens out at once. It actually doesn't. It actually happens in sort of a stepwise fashion as it releases each of those hydrogens. It's actually extremely hard after the first hydrogen that comes off to get that second one off, or if you have a third one, like in the case of phosphoric acid, which has three, it gets even harder and harder to get to that third one to come off. And a couple of things, that happen is, again, hydrogen is H plus. After we release the first one, we have something that is negatively charged, right? So it's going to kind of hold that positive guy a little bit tighter. So it makes it a lot harder for it to come off. And then if you had three hydrogens, you got even larger positive charge after the second one that comes off. So they do come off one at a time. When we talk about an acid and base donating and accepting, they donate or accept really just one H plus at a time. And that's an important sort of idea to remember. Now, there is sort of a consequence of this Bronsted Lowry sort of reaction, and that is when this sort of donation and accepting of an H plus occurs, it actually creates some partners on the other side of the arrow that are related to our acid and bases. So in this particular case, HA is just a generic formula that is sometimes used for an acid. For a monoprotic acid, it has one hydrogen to give. That could be like HCl, it could be like HBr, it could be HNO3, you know, so it's just a kind of a generic formula for an acid. But what's going to happen is essentially this acid is going to send over an H plus there to water in this case, which is acting as a base. So the water is going to accept that H plus and will form H3O plus when it does so. The HA will lose the H plus and form A minus on the other side. So the relationship here is the acid on one side, when it loses that H plus, will make a partner on the other side, which is this conjugate base. The base on the left-hand side, which will accept that H plus, will create a partner on the other side, which is known as the conjugate acid. The absolute only difference between these guys on each side is this guy right here. It is the 1H plus. So that is the only difference that there could be for them to be pairs. When the acid goes to the conjugate base, it is one less H plus. When the base goes to the conjugate acid, it is one more H plus. Again, it makes sense because the acid loses the H plus, so it loses an H plus. The base accepts the H plus, so it gains one more. In terms of acid bases, conjugate acid bases, on the left-hand side of the arrow is pretty much always where you find just your acid and base. On the right-hand side of the arrow is where you find your conjugate acid and conjugate bases. And these are sometimes referred to as conjugate acid base pairs. And again, the absolute only difference there could be if they are considered a pair with each other is 1H plus. That's the only difference there could be. If there's anything more than a 1H plus difference, then they are not pairs. So they have to only be different by 1H plus. And that means you can sometimes figure it out if you have two things and are asked, are these guys kind of pairs? You could either put an H plus on one thing or take off an H plus for one thing, and you should get the other guy that's there. So, you put the H plus on or take it off, and you should find the other guy that's there. If they don't match that way, then they are not pairs. Any questions on that there? So if we look at this here for our HCl in our water, in this case, we have our acid conjugate base pair. Again, the hydrochloric acid should be the one donating the H plus over to the water, which again is acting as the base. So once again, this is our acid, that is our base. When the HCl donates the H plus, this becomes the conjugate base over here. And when the base accepts it, this guy here is our conjugate acid. Yeah. And again, the only difference between those two things is that one H plus that has been transferred. Any questions on that there? So here's again what is sort of going on. We got our acid giving up that H plus over to water, forms the hydronium ion. And again, as I mentioned before, with the water involved, that is where we produce H3O plus. This is really, it is a reaction happening, acid-base reaction, but it's really just basically, so it's really just a solution of hydrochloric acid in this case. but we get our H3O plus and our Cl minus. And again, you can see this guy has one less H plus than that guy. And this one here has one more H plus than what started with water. Try one here. Look at each of these pairs and decide, are these conjugate acid base pairs? So take a minute or two to see what you come up with. So what you're looking at to determine are these pairs is the difference pretty much 1H plus. So that is what we're looking at. So if we look at the first one there, we got like an HClO4 and we got a ClO4 minus. Is this a conjugate acid base pair? It is. The difference here is just one H plus. So if you want, you can put the H plus onto this guy. You get HClO4 plus 1 minus 1 gives you 0, right? So you get the guy on the left there. Or if you take off the H and you become one more negative when you lose the plus, you end up with the ClO4 minus. So whichever way you want to look at it. So at number 2 there, we have HCl and ClO minus. The difference here is 1H plus, but there is also a difference of a oxygen that's here and no oxygen over here. So because of that, it cannot be a pair because it's an H plus difference and an O difference, and it can only be H plus only. Any questions on that one? Looking over here, we got H2PO4 minus. We got an HPO4 2 minus. Are these guys pairs? These guys are pairs. Again, if you want to think about it, you could take off one hydrogen from this, which leaves you just one. And when you lose the plus, you become one more negative. So you go from -1 to -2. So these guys would be a pair. And lastly, HNO3 and NO3 minus, that is also a pair. Again, if you put the H plus onto the NO3 minus, you end up with HNO3. Again, +1 -1 gets 0. So that's where the charge goes away. Any question on any of those there? It looks like everybody but 2 in this case. All right, so for each of these here, why don't you write the conjugate base for each of these? Okay, let's take a look. So hopefully you understand at this point that pretty much the deal here is an H plus. The question is, do we put it on or do we take it off is sort of the question we need to answer. So sometimes, they're not nice enough to tell you what these things are. They just ask for what the conjugate base is or what the conjugate acid is. So it's important to remember what we talked about earlier. On one side, right, we have the acid plus the base, and that makes a conjugate acid and a conjugate base. Now remember that the acid on the left-hand side, its partner on the other side is the conjugate base, while the base on one side, its partner there is the conjugate acid. So if they don't tell us what this is, we know we're looking to write the conjugate base, which means if we follow it backwards here, what we are dealing with in each of these cases are acids. And that means that really all we need to know is the Bronsted Lowry definition of an acid, which is something that will donate an H plus, right? So because we know that these guys are now acids, it should be donating an H plus. So it's really good to understand that relationship, especially in these type of problems. You can kind of think about it backwards. And once you're able to sort of identify what these things are, then you could just go by the basic definition of what an acid or a base is. So with that basic definition, I know now that I need to pretty much take off an H and a plus here. So when I take off the H, I end up with an H and an S. Remember that when you do lose the plus part of it, it does affect the overall charge. So every time you lose a plus, you actually become one more negative. So it was neutral, lost a plus, becomes one more negative, and we end up with HS minus as the conjugate base. Any questions on that there? Same approach for the next one. We're going to take off the H again. That will leave us an S. We also again lost the positive, so we become one more negative. In this case, we actually were -1 to start with, so one more negative would put us at -2 in this case. Here we are going to lose an H, which will leave us a nitrogen with 2 H's. This was also neutral, so we lost the positive as well with it. So this becomes NH2 minus. And lastly, here we're going to take off an H here. So that leaves us 1 H, an S, an O, and a 3. And same idea, no charge, losing the positive for the H plus now makes this HSO3 minus. Any questions on any of those there? So that is really the big key that most people have trouble with is, either put it on or take it off, right? So so that is how you want to kind of think about it backwards as to whether you should put it on or take it off. Now, logic would tell you, obviously, if you have something that doesn't have a hydrogen in it, it can't give it away. So it's a kind of going accepted in that case. Yeah. Is there a question? Yeah, so the idea behind sort of the Bronsted Lowry definition, which creates these acid conjugate base pairs and these pairs that happen, is there's really just a transfer of 1 H plus from the acid to the base. So that means always the difference between like the acid and its conjugate base, or even the base and the conjugate acid, can only really be 1 H plus difference. Yeah, because it is an H plus, so that positive, you're basically kind of losing a positive to become one more. You kind of think of it like, you're losing a proton, right? So then you got more electrons, so you become more negative in that case. And the opposite happens to the person that's accepting the H plus, right? And now when it accepts the H plus, it actually becomes one more positive. So that guy moves in the opposite direction because it gained that HS. So if you think about the water example where the water gained the H plus, the water was neutral to begin with, but when it gained the H plus, it became H3O plus because it gained that really proton coming in. Yeah. So that's also the thing that, a lot of people mess up on is sort of the charge part of it. So sometimes people just think it's just the H, but that plus is really important and it does affect obviously the charge. And as you correctly said, if somebody loses it, they become more negative. But on the other side, the person that gains it becomes more positive. And it's just one more positive or one more negative from where they started. Other questions? In this case, because we're writing the conjugate base, that means everything that we started with was an acid, which means when it loses that H plus, it does become one more negative. Yeah. It would be. So for example, let's just say we were going to do the conjugate acid for our first guy. We'll do this guy, actually, we'll do this one here. So in this particular case, if this was just a question, what is the conjugate acid for this guy here, that HS minus? Again, if you weren't sure what you're dealing with, you could think about it backwards. I want to write the conjugate acid, which means what I am looking at is a base. And the definition of base is it should accept an H plus, which means in this case, we would put the H plus on. And that means in this case, we would add 1 H, so that gives us 2 H2S. And now that plus comes into play here. So +1 and -1 that we started with basically equals 0. So we end up with something that has no charge in this case. So it started out with like a negative charge. I gained that positive, became one more positive, which moved it from like -1 back to 0, basically. Yeah, in terms of the charge. Other questions on that? So why don't we try like HCO3 minus? Why don't you write the conjugate acid? Why don't you also write the conjugate base for this guy? So starting with this guy in both situations, what would be the conjugate acid to the right? What would be the conjugate base to the left there? Okay, let's take a look. We'll go with the conjugate base first. So in this case, I want to write the conjugate base. So again, we're not sure. I know conjugate base is over here, and on the other side is partner is the acid. So in this particular case, an acid will donate the H plus. So the conjugate base actually should have 1 less H plus, which means we take off the H, we're left with CO3. Because we lost the plus, we become one more negative. So we go from -1 to -2, which is carbonate in this case. Yeah. Any question on that one? Now, if we want to start with the same guy, but write the conjugate acid, again, if we weren't sure, the conjugate acid partner on the other side is a base. So that again means that a base should accept the H plus. So in this case, we're going to put the H plus on. When we put the H plus on, we put the H on, we get H2CO3. Again, we have the +1 and -1, which basically equals 0 at this point, and we would end up with carbonic acid in this particular case. Yeah. This guy here and this guy here are partners. This guy here and this guy here are partners. Is this guy and this guy partners? They are not, because this is a 2 hydrogen difference. Yeah, so that's why, because it does come off one at a time, and those guys in the middle, the guy in the middle is really what binds it. Any questions on that? We also just saw this guy in the middle in one case could act as an acid, right? And in one case could act as a base. And there are certain things that can kind of do both, can act either as an acid or a base. And those are what are referred to as amphoteric substances. And they can act as an acid or a base. And very commonly, like we just saw there, like with the HS minus, the HCO3 minus, a lot of times something with an H and a negative charge can pretty much go both ways, can act as an acid or base. Those are guys that very commonly have that ability to do it. The reason they have the ability to do it is because they have an H to give, and they can also have room to kind of accept the H, so they're able to kind of go both ways. Water, as we will see shortly, also is amphoteric. It could go both ways. It could act as an acid or a base. So there are a lot of things that can kind of go both ways, but very commonly the easy way to recognize them in a lot of cases is usually we'll have a hydrogen and probably some type of negative charge, and then it probably has that ability to kind of go both ways, give it away or sort of accept it. Any questions on that there? Any questions on acid conjugate base pairs? Obviously, you need to be able to write those things, right, and identify them. Let's talk a little bit about acid strength. The forward reaction of an acid with water is basically our acid plus our water, making our hydronium and our conjugate base there. In certain cases, the products can go back the other way. And in this situation, we do represent it with those arrows heading in both directions. And if you remember, we saw that with our weak electrolytes. And in a weak electrolyte, like a weak acid, it has the ability basically to go both ways. And I think I said earlier, HF is an example of a weak acid. It can basically go in both directions. And if you remember when we talked about electrolytes and weak electrolytes, and we talked about a little bit earlier today, a weak electrolyte will pretty much stay together. So in solution, unlike a strong acid, this is what you mainly have actually in that solution, but you do have a little bit of these guys. So if you're looking at sort of the beaker in that situation, you would actually have a good amount of HF still together, but you would have a little bit of H plus and F minus sort of floating around. So because it's still able to break apart a little bit and produce a little bit of H plus, still considered an acid, but it's much weaker acid than, as we talked about earlier, with something like hydrochloric acid, which will 100% break apart in solution. Again, you could also represent that reaction by just simply writing it like this without the water. This reaction, they are equivalent to each other. They're basically the same reaction. It's basically just the acid in water. So again, as I mentioned before, those are weak electrolytes. They mainly stay together, but they still have that ability to produce a little bit of those H pluses. And again, because they're able to produce a little bit of those ions, if you remember, like your light bulb went off dimly, right? And that's because there's not a lot of ions floating in a solution, but there's still some. So it's still able to conduct electricity. And in terms of an acid, it's still able to produce H plus. Obviously, if you took a solution of hydrochloric acid and put the light bulb in there, it would be very, very bright because you just produced a lot of H pluses and ions in that solution. Pretty much 100% of it is ions floating around. which again is why it's a much stronger acid than something like hydrofluoric acid here. Now, if the forward direction predominates, the giant arrow, I guess, that is a strong acid, and a strong acid, as we mentioned, is what is sometimes referred to as being completely ionized or completely dissociated. Those are really big words to say. It falls apart 100% into basically ions is really what that means. So again, our hydrochloric acid will 100% break apart into ions. And that is what it means, completely ionized or dissociated. Basically 100% of it just breaks apart. If you think of it like a one-way street, everybody's just dumping out on the right-hand side there. It's all coming out as ions. Nobody's staying together in a strong acid situation. And again, obviously the opposite is true in the weak acid. They're pretty much mainly staying together, and a little bit of it is dumping out into the solution. And obviously HF is an example of that. Nitrous acid is an example. Hydrous ionic acid is another example. The most common example of a weak acid is acetic acid here. You very often come across that's acetic acid. That's basically vinegar. Yeah, C2H4O2, sometimes written like that. But acetic acid is a very common weak acid that you come across a lot. HF as well. And obviously, I think I listed earlier most of those strong acids there: HCl, HNO3, HBr, HI, HClO4. You know, those are pretty much sheer strong acids that we come across. Now, there is sort of a relationship between sort of the acid and its conjugate base, or the base and its conjugate acid. And it's sort of an opposite relationship, which means that if it comes from a strong acid, the conjugate partner is relatively weak. And if it comes from a strong base, its conjugate acid is relatively weak, and vice versa. If it comes from a weak acid, its conjugate base will be relatively strong. And if it comes from a weak base, its conjugate acid will also be relatively strong. The result of that is really nothing that we get into in this class. What it can affect is if you have sort of a conjugate partner on the other side, if it's relatively strong, it can continue to react with something like water and really change the solution to be more acidic or basic, and that can sometimes happen. Again, there's the list of our strong acids, and then earlier we talked about sulfuric acid, which can again donate too. There's also what are sometimes referred to as triprotic acids, and the most common one is phosphoric acid here. It has 3 hydrogens that it could donate, and again, each hydrogen will basically come off one at a time. And that is phosphate, which is why it's called phosphoric acid in this particular case. Any questions on that there? Okay, then let's talk about water as an acid and base. As I mentioned earlier, water is an amphoteric substance. In certain cases, it can act as an acid. In other cases, it could act as a base. So in the first one here, water is acting as an acid. It's going to donate that H plus over there. And the result of that is it's actually going to produce a base here, some hydroxide. In the other case, the water is acting as the base, and it's going to accept the H plus and produce H3O plus. So if you ever see a reaction or an equation and you're not sure whether or not you think it's a acidic sort of solution or a basic solution, looking at the equation, and if you see OH minus on the right-hand side, probably a pretty safe bet that you're dealing with some type of basic solution. If you see H plus or H3O plus on the right-hand side of the arrow, it's probably some type of acid situation that's occurring there. H3O plus or even H plus on that side is typically an acid. Water is crazy enough, it will react with itself. It's pretty much what happens when you have water, because it's bored, it's got nothing else to do, so it decides, why not, let's just react. So one water acts as an acid, the other one acts as a base. Yes, that is the conversation that occurs. So we'll say this guy is the acid, which means it will donate the H plus over to that water that would act as a base. and it will create H3O plus and OH minus. It's actually a reversible sort of reaction here, which means this is a weak electrolyte, and it will actually create what is referred to as an equilibrium. And then an equilibrium will be set up with water. And basically what an equilibrium is, because there is a forward direction that goes that way, heading towards the reactant side, and a reverse direction that is going in the opposite direction. When something reaches chemical equilibrium, what it means is the rate of the forward direction will equal the rate of the reverse direction. It does not mean that you have equal amounts on both sides. It just means just as quick as it goes to the right, it's going to come back the other way just as quick. What that essentially does is if something's going back and forth at the exact same rate, it will pretty much lock into place where everybody's at that point. So when it reaches equilibrium, whatever everybody's concentrations are at that point, they basically will be maintained, because as soon as it loses a little bit, it comes back, loses a little bit, it comes back, and they're able to basically maintain wherever they're at. And again, it doesn't mean that they're equal to each other. Sometimes people think chemical equilibrium, where you are equal on both sides. It doesn't mean that. It just means really the rate at which is going back and forth is equal to each other. And that again just sort of locks everybody into place in terms of their concentrations, wherever that may be at that particular point in time. Because of that, you could write an equilibrium constant, which we don't talk about until the end of this chapter, but years ago we already talked about this. But you can write a relationship that is known as Kw. Kw is really the equilibrium constant for water. And it does provide us a useful relationship to calculate whether or not a solution is sort of acidic or basic. So Kw is equal to the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. When you see little brackets like that, that means concentration. And pretty much what that means is molarity, which is our moles per liter is what we're talking about here. So this is our first of many formulas that I talked about earlier. Some books will use H3O plus, but you could just as easily use H plus. So again, same deal, exact same. Whichever one you like, you can use. It don't really matter. But basically, the H plus is the acid part of the solution. The OH minus is like the basic part of the solution. So you could use this to calculate, if you know what the acid part of the solution is, concentration, or the basic part of the solution. You could use this relationship here to calculate what the other guy's concentration is. And you could compare the two and decide whether or not that solution is acidic, basic, or neutral. It says at 25 degrees Celsius for a couple of reasons. One reason is it is what is known as an equilibrium constant, and the value of the equilibrium constant actually does change with temperature. So it is actually different values depending on the temperature. But for our purposes and most purposes that you would use this number for, it's always 1 times 10 to the minus 14. And if you see something like at 25 degrees, you could kind of ignore it for all the purposes of the calculation. It's just kind of telling you a sort of standard temperature. You can use this number and stuff like that. So there is a relationship between, as I wrote over it, so I'll write up here, between the concentration of H plus and the concentration of OH minus. So basically, as one goes up, the other goes down. So as the H plus concentration goes up, the OH minus concentration goes down, and vice versa. As the H plus concentration goes down, the OH minus concentration goes up. When they are equal to each other, that is pretty much when you have a neutral solution. You have 1 times 10 to the minus 7 for each of them, and they are equal to each other and neutral. But again, as the H plus goes up, the OH minus goes down, and vice versa. And depending on which one is larger as to what type of solution you have, acidic, basic, or neutral. So we can compare these two things. If you should calculate the H plus concentration and it is larger than the OH minus concentration, so essentially the acid part is larger than the base part, the solution will be acidic. If you calculate that the OH minus part is larger than the H plus part, really the basic part here is larger than the acid part, it is going to be a basic solution. And like I said before, if they are dead equal to each other, That means they both will have 1 times 10 to the minus 7 molar as their concentration. And it would be a neutral solution in that case. So to do the calculations, the good news is this is the same calculation regardless of which one you're given. You're going to take 1 times 10 to the minus 14, which is the value for Kw. And by the way, you always have that number. So 1 times 10 to the minus 14 is the number you always have. And you're going to divide it by either the OH minus concentration, and that will give you the H plus, or you're going to take 1 times 10 to the minus 14 divided by the H plus concentration, give you the OH minus concentration. Super important to make sure that you use your exponent button in this chapter, or you're going to have a very long chapter. Yes. So make sure that you definitely 100% use that exponent button like we talked about at the beginning of the semester. Do you have a question? Yeah. Yeah, so it basically means concentration, and for the most part, that means molarity. So that means basically the molarity of the H plus or the molarity of the OH minus, which is moles per liter. Yeah. So the H just means moles per liter? Not the H, but it's actually the bracket. So when you see anything on brackets, the bracket part means concentration, and what that bracket usually means is molarity, which is our moles per liter. So whatever's inside it, we're talking about the molarity of whatever's written inside. So when we have the H plus written inside, we're talking about the concentration of the molarity of the H plus, or if we have the OH minus written inside, we're talking about the concentration of the OH minus in that solution. And what we're really talking about is in a solution, what the concentration or molarity of all those free floating H pluses in that solution are all the free floating OH minuses if we're doing the other guy. The concentration of what it is in that solution, basically. So, other questions? Yeah. Yeah, so you will do a calculation, and we'll do some here in just a second, but you'll do a calculation here and you'll eventually end up with 2 numbers. One probably given to you, either the H plus concentration or the OH minus concentration, and then you would calculate the other pretty much. And when you get those 2 numbers, you would look at them and compare them. And if you look at them and the H plus concentration that you calculated or were given to you is larger than the OH minus concentration, then it means that that's an acidic solution. And that's because you could think of H plus as like the acid part of the solution, and the OH minus like the base part of the solution. So if you calculate that the H plus part, the acid part, is larger than the OH minus, then the solution would be acidic. And vice versa, if you calculate that the OH minus concentration, which is really the base part of the solution, is larger than the H plus concentration, then it would be a basic solution. And if they were dead even, they would have a concentration of 1 times 10 to the minus 7, and that would be a neutral solution. Could they kind of cancel each other out if you want to think about it that way? They're dead even, got about the same amount of each of those guys in there. And that's really what makes something more of an acidic solution versus a basic solution is if you have more H plus floating around, it's going to be an acidic solution versus OH minus, or if you have more OH minus floating around, it's going to be a more basic solution than obviously an acidic solution in that case. Other questions? All right, well, nothing better than let us do some here, yes? All right. Well, we start with the first one there. We have the H plus concentration is 3 point, well, we just start with that one. H plus concentration is 3.4 times 10 to the minus 4. What is the OH minus concentration in this case? And is it acidic, basic, or neutral? Grab your calculator. Make sure you know how to punch it in correctly. I will grab both of my calculators. Take a look. So really what we're using here, just so everybody's clear, is we are using that relationship of Kw, which is the concentration of H plus times the concentration of OH minus. And again, that equals for our purposes always 1 times 10 to the minus 14. In this particular case, they gave us the H plus concentration, which means we could solve for the OH minus concentration by simply just dividing the H plus to the other side. So the H plus concentration would equal 1 times 10 to the minus 14 divided by the, I did the wrong backwards there. Sorry, try it again. Take 2. We are looking for the OH minus concentration, right? Yep. There we go. Try that there. All right. The OH minus concentration, which would be good, is divided by the H plus concentration. So it's really the same calculation regardless of which one you're given. You're going to take 1 times 10 to the minus 14 and divide it by what you were given. So that would give us 1 times 10 to the minus 14 divided by 3.4 times 10 to the minus 4. So just a reminder, we want to go 1, we want to go exponent button, we want to go negative button, and we want to go 14. We want to divide. We want to go 3.4 exponent button, negative button, and 4, and hit equals. If you do all that, you get a number. Looks like 2.9 times 10 to the minus 11. And this is a concentration, so it would have molarity at the end of it. And that would be the concentration, first off, of the OH minus. Any questions on that there? Again, like normal, and you'll see it a lot more than before. If you find yourself looking at a number at the end and the front part looks good, but the exponent part does not look good, it's off by a few. It's probably the way you're punching it into your calculator. And it will be magnified in this chapter because we're doing some things with logs a little bit later on and other stuff as well. But first off, any questions on that calculation? Now, is the solution acidic, basic, or neutral? So remember, at this point, we now know that the H plus concentration is this guy. This is the OH minus concentration. Is it acidic, basic, or neutral? Which one is larger? Are they equal to each other? That's good. Okay, we're down to a 50-50 shot here, right? So which one is larger, the H plus or the OH minus? It is what I heard. It is the H plus concentration is larger in this case. The H plus concentration is larger than the OH minus concentration, which means the solution would be acidic. A reminder that when you look at the exponents, the negative is important there, because when you have a negative exponent, the smaller number is actually the larger. And what that means is when we say to the minus 4, we're going 4 places this way and putting zeros. When we say to the minus 11, we're going 11 places this way and putting zeros, which makes it a much, much smaller number. So when you're comparing these things, remember that if you have negative exponents, the actual smaller negative exponent is actually the larger number when you're doing the comparison there. Question? Yeah. 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 So you should end up with the same number. My guess is somewhere there where you're punching it in, you're maybe doing something extra. Just come up in just a second. I'll be happy to look at it. But the other common thing that people will do is hit the multiplication button. Remember, you shouldn't use the multiplication button when you're using your exponent button. You shouldn't be using the inverse log button or shift log, because we'll actually be using that a little bit later on correctly in this chapter. But you should just use that exponent button and you should hopefully be okay. Any questions on that there? I think it's probably a good, yeah. Yeah, so again, you'll sometimes see 25 degrees Celsius. It's really just telling you that you could use that 1 times 10 to the minus 14. As I mentioned before, it technically does change with temperature, but pretty much every problem you probably do, you could assume it's 25 degrees. If it does say 25 degrees, you don't have to use it anywhere in the calculation. Yeah. If it doesn't say 25 degrees, you could just assume it usually is.